All right, so with chapter 6, we're going to be looking at the subatomic particle, the electron, so the negatively charged particle, and we're going to be looking at sort of the behavior of the electron, um, and then how we can define specific electrons within a given atom. So we think about, for instance, just a sodium atom, atomic number 11. It's going to have 11 electrons. We'll ultimately be able to see how we can sort of specify which electron we're actually referring to. But to start, we're going to be looking at waves because we're going to see throughout this process that the electron, we think of it as a particle, but it's also going to be able to behave like a wave. And with waves, typically we think about them in terms of electromagnetic radiation. So visible light, for instance, ultraviolet rays, infrared, all of those are going to be types of electromagnetic radiation. And they're all going to have waves, or they're all going to be waves, essentially. And when we're looking at a wave, we've got a couple different sort of characteristics that we may be interested in. So one of them being the amplitude, just essentially the height of that wave. So if you look here, kind of just got an axis, and then we've got the peak and the trough, so the bottom piece here. So the amplitude is just going to be sort of the height of that wave. So if it was a larger wave, we would have a larger amplitude there. And the wavelength, this is going to be more of what we focus on is the wavelength. But the wavelength is just going to tell us, as it would suggest, the length of that wave. And the way that we determine that is by taking essentially two of the exact same points on adjacent waves. So in this case, we're looking at the peak of each of these waves and the distance between those two. But with the wavelength, it doesn't necessarily have to be the peak. We could have done the same thing with the trough at the bottom, or we could have picked sort of the midpoint here and then gone to the midpoint there. So it's just going to be the same point on two adjacent waves, just see the distance between those. And then depending on the wavelength, that's going to affect what's known as the frequency. So if we look at these two waves here, the top one has a much shorter wavelength because if we go from peak to peak, there's a much smaller distance than with the one at the bottom. So we've essentially got about 3 wavelengths on the top for every 1 wavelength on the bottom. And that's going to affect the frequency because with these waves, what we're going to see is that they're going to travel at the same velocity. So all light travels at the same speed if it's going through the same medium. So obviously, if we have light going through water versus air, they're going to travel differently. But if we've got 2 different waves just traveling through air, they're going to be going at the same speed. So what we're going to see is that frequency, the amount of times that these waves repeat, is going to increase as the wavelength decreases. So we can see a shorter wavelength on the top here. So we have more frequency. We can see these waves are repeating much more often than the longer wavelength at the bottom there. And just to go back for a second, with wavelength, since it's a distance, we're going to have some sort of distance unit. So in a lot of the equations, we'll have to put meters. But with a lot of the waves that we're going to be looking at with visible light in particular, we're going to be using nanometer instead. So nano just means 10 to the negative 9th. So it's just going to be a it's a 1 billionth of a meter. And then with the frequency, this is going to be how often these waves repeat in a given amount of time. So typically, we're going to be using the unit inverse second. So the s for second, and then raised to the -1 power. Or we can think of it, if I get the pen working here. So it could be inverse second, like that, which is the same thing as just making second on the bottom of the fraction. And then in some cases, you may also see, and you may have heard this term before, hertz, so Hz, are all going to mean the same thing. So when we're looking at frequency, these are the units we're going to be utilizing for that. And then, like I said, often, excuse me, often when we're looking at electromagnetic radiation, or often when we're thinking about waves, rather, we're going to be looking at electromagnetic radiation. So with it, if we see here, just this little section that kind of got brought out to the front here, that little visible section is just going to be the visible region of electromagnetic radiation. So the wavelengths that we can actually perceive with our eyes. And then on each side of that, we've got different types of waves. So ultraviolet, we think about the sun, can cause sunburns, can cause skin cancer and things like that, because the ultraviolet rays are going to be higher energy, so they can actually damage the DNA. Similarly with X-rays. So if we look at the bottom here, frequency, we can see the frequency is increasing to the left here. And what we're going to see as we go through this, energy is going to be directly related to frequency. So as the frequency goes up, the energy is going to increase as well. So with the X-rays, these are going to be even higher energy now. And when you get an X-ray at a doctor or something, so if you break a bone and you need to get the X-ray done, since you're only going to be getting that done like once, and you're not typically going to have to get X-rays very frequently throughout your life, the amount of radiation that we're being exposed to there typically isn't going to be harmful at all. But then if you think about the X-ray technician, they're going to be doing that multiple times a day, multiple days a week for the entire year, or however often they're going to be working there. So that's why typically the X-ray tech is going to be in some sort of different room, just so that they're not constantly exposed to these higher energy wavelengths. And then on the opposite side, we can see infrared. So if you think about the visible region for a second, so kind of Roy G. Biv, and then on the end, we've got the V for violet. So that's why we've got ultraviolet just a little bit further than that. And then with the red, on the longer wavelength side of that, we have infrared. So you can kind of see where those terms are coming from there, as well as microwave and then radio frequency. But again, wavelength and frequency are going to be inversely related. So that's why in this case, wavelength is increasing to the right, but frequency is increasing to the left. But like I said earlier, any type of electromagnetic radiation, so any type of light, is going to be traveling at the same speed if it's going through the same medium. So if we had a vacuum, so something like space, for instance, and we had X-rays, visible light, infrared, any of those types of waves passing through space, they're all going to be moving at the same speed, but they're going to have a different wavelength, they're going to have a different frequency. But the product of those, if we look at this equation at the bottom, the product of those is just going to give us that speed of light. And if we take any of those frequencies, any of those wavelengths, and multiply them, what we're going to see is that speed of light in a vacuum is going to be just about 3.00 times 10 to the 8th meters per second. So that's going to be 30 million meters for every 1 second. Or actually, that'll be 300 million, excuse me. 300 million meters for every second. So if you think about a light year, the term itself is a little bit misleading because we've got year in there, but light year is actually going to be referring to a length of distance. And with it, it's just the amount of distance that the amount of distance light's going to travel in 1 year. And if you think about it, it's going to be an extremely, it's unfathomably large, because for every 1 second, that light's going to travel 300 million meters. And then there's going to be 60 times 60 times 24 times 365. So there's going to be, what is that? 31,536,000 seconds in a year. And then for every one of those seconds, it's going to travel 300 million meters. So that means in a light year, the distance traveled by light is going to be 9.5 times 10 to the 14th meters. So an extremely, extremely large number. Because that would be billion, trillion, be almost 10 quadrillion meters in a year. And then with light, with these waves, we're going to see that there's different sort of processes or yeah, I think processes is a good enough word. That can happen. And when we're looking at light in particular, one of those is going to be refraction. So if we see here, and it's kind of similar if you've ever seen the Pink Floyd album cover, it's essentially the same thing being shown on that one. But we've got a beam of light, and then it travels through a prism. And now that when it gets into the prism, this is a different medium. So now it's not traveling through just the air. Now it's traveling through this glass or whatever it's going to be. So the speed of light is actually going to change in this substance. And there's actually going to be what's known as the refractive index, which is going to be dependent on the wavelength. So what we're going to see is that when the light hits this prism, those different wavelengths are actually going to separate out. And that's why when we see the light being produced on the other side, or the light that's leaving the prism, that's why we kind of see this rainbow effect. It's going to be because of that process of refraction. And then when we've got, actually diffraction first. So a similar process to, not that similar actually, but another process that these waves can undergo is going to be diffraction. So if we look here, these waves are traveling towards this barrier with these two narrow slits. So you can kind of see those yellow sort of bumps here in those two spots. So as we have these waves travel in this direction, the only spot they're going to be able to pass through this barrier is just going to be in those narrow slits. And what we're going to see then is on the opposite side, is we're going to have, instead of just a continuous thing of light being produced, so if this is just our screen or wherever we're having that light hit at the end, we're not going to see a continuous thing of light being produced here, because with the process of diffraction, the waves themselves are actually going to bend. So that's why when we're looking here, we now see kind of those spherical shapes, or at least half spherical. And since we've got two of them, these waves are now going to either add or subtract from each other, depending on exactly how they add up. So with the yellow ones, this is where we would actually see light being produced, or whatever it's going to be, depending on the wave, I guess. But this would be an example of constructive interference, because what's going to happen in this case is the waves in this spot are going to add together, because the waves themselves are going to be in sync. So if we look at the two waves, and again, it's because we've got two slits here. So we bend the light twice, essentially. But when the light adds up, it's going to be because the waves are in sync. So you see we've got the peaks matching up, troughs matching up as well. So when we take these two waves and combine them, the top and the bottom part, since everything above this line is above it in both of them, we wind up with a larger amplitude. So the wave itself essentially just doubles in size. Whereas the dark spots here, we're not going to see any light in those areas because of destructive interference. And now with these waves, they're going to be out of sync. So if we look at it, for the first one, it starts on the top. The second one starts on the bottom. And then they kind of just alternate from there. So what we're going to see is these waves essentially cancel each other out. And that's why we're not seeing anything show up in those locations. So with diffraction, we're thinking about essentially just bending the light as it passes through a small opening. Refraction, the previous one, is going to be bending the light as it passes into a new medium. And the medium is just referring to whatever that wave is traveling through. So in space, it's essentially a vacuum because there's really nothing there. On Earth, passing through the air. And a lot of the times we'll just use the speed of light in the vacuum because they're going to be close enough anyway. But then if it's traveling through water or traveling through the prism, that's going to be a different medium. So it's going to travel at a different speed. we're going to see those waves bend accordingly. And then again, with the interference part, we just want to think about if those waves are going to add up or if they're going to subtract from each other. So when they're in sync, and it doesn't necessarily even have to be perfectly in sync, but if we offset this one by just a little, we would still have, like if we want to think of the top as the positive, bottom as the negative, we would still have the positive pieces mostly matching up, still have the negative pieces mostly matching up. So we'd still wind up with something similar to this. It's just not if it's not perfectly in sync, it won't just automatically double. We'll see a little bit of destructive interference in some spots, because if you think about just moving this bottom wave a little bit to the right, they'll be in sync to a certain point, but then they'll be out of sync for a little bit. So we'll still have some constructive interference for the most part, but there'll be a little bit of destructive interference in that case as well. Similarly, if we take these two waves at the bottom and just offset one of them by a little bit, it'll still primarily be destructive, but there'll be a little bit of the positive kind of overlap where they're adding together. But these two are just sort of the most extreme scenarios where we've got perfectly in sync or perfectly out of sync. And then with this, we've also got the black body radiation. So if you look here, this is just going to be some molten liquid metal. And with it, since it's so hot, it's actually starting to produce light itself. What we're going to see is that the wave nature of light just doesn't totally explain this. And the reason why is because light, you may be familiar with the duality of light. What we're going to see is light itself is going to behave like a wave, but it's also going to have particle-like properties too. And we're going to see the same thing with electrons. So typically we think of them as particles, but they'll also be able to behave like a wave. So we'll have the duality of both of those things. And then with this idea, with this duality, we've got what's known as quantum. So if you've seen any sort of sci-fi futuristic type of movie, a lot of the times they just throw quantum in there without really using it correctly. I think Ant-Man might, I haven't seen it, but I think it kind of is a little bit closer, but it's still probably wrong. But with quantum, what we're going to be referring to is just specific energy levels. So with this quantum, we can only have essentially specific values for something that's quantized. And with it, we're primarily going to be thinking of energy. So there's going to be specific amounts of energy that are either going to be able to be absorbed or emitted. And then with those amounts of energy, we can just refer to them as the quanta. But with this, we will start to get into a little bit of the quantum theory and quantum mechanics and things like that. But we're only going to touch on it a little bit. We're not going to go super in depth. If you wind up taking like a physical chemistry course or something like that, you'll definitely spend a lot of time on things like this. But like I said, with these quantized values, they're going to be specific numbers. And what Max Planck was able to do is essentially determine sort of what these values are going to have to be. And based on that, he named it after himself, Planck's constant or Planck's constant. I'm never really sure which one it is. I think Planck because he's, I believe, German. But if you say Planck, I think everybody would probably know what you're referring to. But with this, what we're going to see is that with radiation, so if we're thinking about the electromagnetic spectrum or anything like that, the energy of a quantum of radiation, so a quantum, again, just the smallest quantity that we can have, is going to be equal to Planck's constant. So just right here, 6.626, and then we've got more digits there, times 10 to the negative 34th. And then the units on this is going to be joule second. but the energy of the smallest amount of radiation we can have is going to be equal to that constant times whatever the frequency is. So remember previously I said, when we were looking at the spectrum, I said that energy and frequency are directly related. So that's why as we moved further to the left on that spectrum, the frequency was increasing. So those were becoming higher and higher energy. That's where we saw the ultraviolet and the X-rays, because those are going to be the higher energy waves. And then with this, if we think back to our, oh, we haven't actually seen it yet. What we're going to be able to do is take this equation, and instead of frequency, just plug in the speed of light divided by the wavelength, because that's going to be equal to the frequency. So we've got a couple different versions of this if we need to figure out the energy of radiation. And with this, we'll also, we won't really look at it at all, but this is going to be referring to one quantum of radiation. So we'll ultimately see that's called a photon. But there's going to be a very similar equation. If we had multiple photons, we could throw an N on the right side of this. So we could have NHV, where N is just referring to the moles of radiation. So the moles of photons that we actually have. But we're just going to be using it in this form here. And then if we look at these two equations, we can kind of see how we can arrive at the one at the bottom here. So HC over wavelength. So the lambda sign, so that upside down Y is lambda, and that's going to be referring to the wavelength. So with it, the speed of light times wavelength times frequency, or the speed of light is the wavelength times frequency. If we think about the units there, wavelength, we're going to have in meters. And then frequency, we're going to have in per second, or inverse seconds, however you want to describe it. So we're going to see wavelength times frequency gives us meters per second. And that's what we want for the speed of light, how much distance is being covered in some amount of time. And then with the energy equation, we've got joule seconds for the Planck's constant, and then just per second for the frequency. So we're going to see that the seconds is going to cancel, and we'll just be left with joules there. So with this, the units, of course, just like with pretty much every equation, are going to be important, but we can also use those units to kind of see how these equations work, how they relate those different quantities. Now, so take a minute on your own to see if you can determine what the energy of one photon. So again, that's going to be a quantum of radiation. That's just going to be referring to essentially the smallest beam of light we could possibly have. But if that photon was for yellow light, might have a wavelength of 589 nanometers. And with this, nanometer is equal to 10 to the negative 9th. So nano anything is going to be 10 to the negative 9th. So a nanometer would just be 10 to the negative 9th of meters itself. But see if you can use the equation that we just looked at. Energy is equal to Planck's constant times frequency. Speed of light is equal to frequency times wavelength. See if you can use those to determine what the energy of this photon would be. And then with it, if you want, and I would recommend you practice on your own just so you can kind of give yourself a chance to go through it yourself. But I'd recommend, as always, just pausing it, because I'm going to move ahead and just show the setup and how we can actually get to the answer for this one. But again, if we go back for just a second here. In this case, for that question, we were given the wavelength, not the frequency. So there's a couple ways we could approach it. We know the speed of light, that's just going to be a constant. We were given the wavelength, so we have lambda. we could solve for nu. So with this frequency, it looks like a V, but it's actually nu, the Greek letter. So we could solve for that nu and then plug it into the energy equation. Or we can kind of do the substitution and just do all of that in one step. So if we rearrange the speed of light, solve for nu, we're going to divide both sides by lambda. So nu is equal to c over lambda. We can plug that into the energy equation and just get this. And now if we think about the information we need for that question, Planck's constant we have right here. I would recommend just doing it to the 6, so 6.626, and then you don't need to really worry about the remaining numbers there. Speed of light, I would just do 3.00 times 10 to the 8th meters per second. And then we were given the wavelength. But for this question, we just got to remember to convert the wavelength into meters. So we should get 5.8 times 10 to the negative 7th meters instead of 589 nanometers. And then we can go through, plug all those in, and we'll see that the energy of that photon is going to be very, very small. So 3.37 times 10 to the negative 19th joules. And with this equation, you can always double check just to make sure in the right ballpark by just looking at the exponents. So on the top, since we're multiplying these together, we're going to add these exponents. So we should wind up with negative 26. And then we're dividing, so we're going to subtract it. But since we're subtracting a negative, it's really the same as adding 7. So since we have negative 26 on top plus 7, we should get negative 19. And that's what we have here. And as long as you're within 1 order of magnitude, maybe 2, but as long as you're pretty close to that exponent, it's a good indicator that you likely did the calculation correct. But if we did 6.626 times 10 to the negative 34th times the speed of light, and then accidentally multiplied the wavelength instead of dividing it, now we would subtract a negative 7 from the negative 26 we had on top. So we'd wind up with negative 33. So we can at least kind of check to make sure we're heading in the right direction with those exponents. And then with this next one, kind of the same idea. In this case, we're given the frequency. We want to determine what the wavelength is going to be. And then we're given the speed of light and Planck's constant again. And then for the second part, we want to determine what the energy of this wavelength is going to be. 1 photon of this wavelength, I should say. So with the top part, we can use the speed of light equation. C is equal to lambda nu. We know what the speed of light always is. We know what the frequency is in this case. So we can take those and rearrange them to just solve for the lambda. So C over frequency. And what we're going to have is 4.55 times 10 to the negative 7 meters. Or we could convert that to 455 nanometers. And with it, typically, with the visible light, 450 nanometers to 800 nanometers, I believe. I might be off a little bit with that range. But it's like 400 to 800 approximately. I don't know exactly the cutoffs. I can't remember it off the top of my head. But with it, typically, with the visible light at least, we refer to those in nanometers just because we have nice whole numbers and don't have to worry about the decimal, don't have to worry about the scientific notation. But with this one, it doesn't specify a unit and it actually has wavelength spelled incorrectly. But it doesn't specify a unit. So you could have either one of these. I guess technically you could convert it the opposite direction into kilometers for whatever reason. But with it, that's why often you'll see the nanometers is going to be the wavelength that's expressed. But with the equation itself, we solve for meters just because the speed of light is in meters. So when we divide by this frequency, we're going to cancel out those seconds, and we're just left with meters there. And then for the second part, we don't even need the first thing that we just solved for, because for the second one, we're looking for the energy. So we need Planck's constant, we need the frequency, and we were given both of those pieces of information just in the question. So we can just take Planck's constant, multiply it by that frequency, and we're going to see the energy of this wavelength, 4.36 times 10 to the negative 19th joules. And then the particle nature of these this electromagnetic radiation can be used to explain what's known as the photoelectric effect. And again, I've already kind of used the term photons. But this is just going to be referring to the radiation sort of as if it was a particle. So rather than thinking of it as a wave, the photon is going to be thinking of that radiation as a tiny particle. So one photon would just be the tiniest beam of light that we could possibly have, essentially. But the photoelectric effect, if we look at the picture here, we've just got some metal surface, and what we can do is hit it with some radiation. And if that radiation is strong enough, high enough energy, what we're going to see is it's essentially going to knock off some electrons. And we see the same thing at the picture here. In this case, the energy is coming, hitting that metal surface. It's going to kick off that negative electron. So what they have here is just a positive terminal. It's going to attract that negative electron. And then we can use that to essentially sort of have a little circuit going on here. And then the electron just travels through. We can measure the voltage, have it come up to the top there. But again, with this photoelectric effect, this only can be explained if we're thinking about radiation as a particle rather than a wave. So again, we're thinking of sort of that duality. Could be thought of as a particle, could be thought of as a wave, because it's going to have behavior, it's going to have characteristics of both of those things. And then the next piece we're going to be looking at is what's known as line spectra. So these are essentially going to be emissions that are produced from different substances. And with emissions, we're going to be thinking about electromagnetic radiation. And depending on the substance, it's going to occur at a, that radiation that's being emitted is going to occur at specific wavelengths. So in some cases, you could even use it to identify what's present in a sample or something like that. But if we look at the picture here, what we're going to see is a flame that we could put sodium in. And then if we think about, and we could put anything in really, but we're just using sodium in the example. If we think about the black body radiation, it's going to emit radiation when it's heated up enough. So what we can do is use a focusing slit just to direct that radiation at a prism. So if you think about it, with this sodium, when it's emitting that radiation, it's really going to emit it in every direction. But we can focus just a little bit of it by having a slit here, just to only let some of it through. We're going to have it hit the prism. And then with it, those different wavelengths now are going to refract differently. So that's why we're going to, if you think back to the Pink Floyd album cover looking one, we kind of get the full rainbow, because in that case, we're using white light that's going to have all of the different wavelengths present. So that's why we wound up with that continuous sort of rainbow spectra being produced. But in this case, it's only going to have specific wavelengths. So we've only got a couple wavelengths coming through here. They hit the prism. They still separate in the same sort of manner. But now that we've only got a couple of those wavelengths, we only see lines at specific sort of spots. And based on the way we set this up, we can actually measure what those wavelengths are going to be. So for sodium, we're going to see wavelengths at 589 nanometers and then 589.6. But then if we look at hydrogen, different element, different substance, going to produce a different spectra. And in this case, we're going to have a few at those lower wavelengths. So what is that? 410, 435 maybe, 486, and 655 maybe, just approximately. But again, with these different substances, the spectrum that they produce is going to be unique to whatever that substance is. And again, the reason we're actually just seeing only a couple spectra rather than a full rainbow like we did with the previous prism is because the previous one, we were assuming it was white light being used. So it's going to allow every wavelength to then be separated out. But in the case of these elements, they're only going to be producing a few wavelengths when we heat them up. And that's why we're only seeing a few spots on these spectra. Yeah. And then if you look at the range here, I said 400 to 800 before. So it looks like the wavelength for the visible region is going to be 400 to 700 nanometers. And then again, just got these different elements. So we do see some overlap here. So if we look at the higher wavelength one for hydrogen, we're going to have that overlap with the neon here. Same thing with the helium. We're going to have some overlap. So if we had a lot of elements in a sub sample, might be hard to differentiate them all because they're all going to be kind of overlapped then. But if we just had these pure elements, we could use this as an identifying technique. And then with this, we'll actually see a little bit later on exactly what's kind of occurring. But these transitions or these spectra that are produced are always going to be specific to that element. So if we did this with a different helium atom or a different hydrogen atom, we're still going to see those same spectra. And then in the late 1800s, a Swiss scientist, Johann Balmer, developed a equation, so how we could actually determine what the wavelength of the spectra for hydrogen is going to be. And then similarly, Johannes Rydberg came along and then kind of adjusted that equation to be a little bit more inclusive of the entire hydrogen spectrum. But with it, they're very similar. So if we look at the parenthesis here, 1 over n1 squared minus 1 over n2 squared, got essentially did the same thing here. It's just in this case, n1 is always going to be equal to 2, which won't always be the case in the Rydberg equation. But with it, we have this equation to solve for wavelength here. So if we know what n is in each of these, and we'll see that a little bit later on, maybe the next couple slides. I thought it was the next one, but it'll be in a couple. But n is essentially just going to be referring to an energy level. And then depending on the energy level, those are going to be quantized as well. Depending on the energy level transfer, that'll determine what the wavelength of light being emitted is going to be. And like I said, with quantum anything, what we're really kind of thinking of is the smallest possible amount. And then we're going to have specific amounts above that, so specific energy levels, greater energy, but it's going to be specific values. So if we go back to this equation for a second, n1 and n2 are going to be referring to the energy levels at which the electron could be located. What we're going to see is that the energy of those levels is going to be very specific. So if we had the first energy level, the second energy level, the third energy level, what we'll see with Bohr's model for electrons is that the electron can move between those different levels, but it's always going to be absorbing or emitting a specific amount of energy so that it's always moving directly between those different levels. So we'll never have an electron that's kind of just hanging out in between two energy levels. It'll always be at one specific, it'll always be at a specific energy level. And we'll kind of see as we go through this, how that electron can move to a higher or lower energy level and what kind of occurs with that process. But throughout the rest of this chapter, we're going to be looking at different quantum numbers. And like I said at the very beginning, we're going to be able to describe the specific sort of location, specific details of each electron in a given atom. And the way we're going to be able to do that is with these different quantum numbers. So the first one we're going to be looking at, the principal quantum number, is really just what n is. And that's going to be referring to the energy level itself. And again, those are going to be very specific energies. And the electron is either going to absorb or emit those amounts of energy as it moves between the different energy levels. So if we look here, 1, 2, 3, 4, all the way up for n, and there's really no limit on it. Because when we have n go to the infinite energy level, what that really just means is the electron's been lost to ionization. Now we're going to have a positive charge on whatever that atom was because it lost the electron. But with these energy levels, like we see here, they're all going to be whole numbers. And the electrons can transfer. In this case, we're showing the electron would actually be emitting energy, because in all of these cases, it's going from a higher energy to a lower level. But what we're seeing in each case is it's starting at some energy level. So 6, 5, 4, 3, 2, whatever it's going to be for all of these, it's starting right at one of those energy levels. And then as it moves to a lower level, it stops right at one of those energy levels. So Lyman series is just going to be referring to any movement of electron that results in it going to n equals 1. So that first energy level. Balmer series, this is the same idea. It's just now going from a higher energy level to the second energy level. And then the Paschen series, same kind of thing. It's just now we're finishing at the third energy level. And like I said before, these transitions, in this case, since they're going from higher to lower energy, if we think about energy in general, like the previous chapter, can't be created or destroyed. Can be transferred forms, can move from system to surrounding, so we can change the energy in a specific location, but within the universe, it's always going to be constant. So if we look at any of these transitions, again, high energy to low, so the electron itself is losing that energy, but the energy can't just disappear into space. It's got to be released in some form. And if we look at the bottom, we can see exactly what that's going to be. So with the Lyman series, we're going to have ultraviolet light being produced, or emitted, I should say. With the Balmer series, this is going to be our visible emissions. And then the Paschen series, we're going to have infrared. And if we look at the size of these transitions, we can kind of see why that's going to be. Because the energy being lost in the Lyman series, much larger than the visible, or the Balmer series, excuse me, which is still larger than the Paschen series. And if we think back to that spectrum, further to the left was higher energy. So we had visible kind of in the middle, ultraviolet to the left of that. So since we're emitting more energy, we're getting a higher energy photon in the Lyman series. And then with the Paschen series, it's just the reverse. We're emitting a lower amount of energy. So we're going to get a lower amount of, or a lower energy form of radiation being emitted in that case. So for this example, we want to determine what wavelength of light is going to be emitted if it's looking at the N1 to, or 2 to 3 transition here. So if we go back and look at our equation here, so N1 is going to be sort of the energy level that the electron is moving to. N2 is going to be the one it's starting at. So when we plug that in, we're going to have 1 over 2 squared minus 1 over 3 squared as our sort of variable piece, because this is just going to be a constant. It's 1.0097 times 10 to the negative second inverse nanometers. And then when we go through and actually solve for it, we're going to see we're going to hit 713 nanometers here. So with this one, just recognize that in this case, our unit actually will be nanometers, because in the equation itself, we've got inverse nanometers. And then on the left-hand side, we've got wavelength on the bottom. So we've essentially just got to flip everything. So that's going to be why in this case, we'll have nanometers there. And let me just check one thing quick. Okay. And with it, just because if we go back, okay, go back further than I thought. With this 400 to 700, the visible spectrum is actually going to, seems like there is a little bit of a disagreement on exactly what's considered the visible, but sometimes it's going to also include like 750. So the human eye can actually see a little bit below 400, a little bit above 700. So with the exact sort of cutoff for the spectrum, it does seem like there is a little bit of variation on what exactly we're considering the range there. Okay. And if we think about the transitions we were just talking about, we can use that to kind of describe the Bohr model for electrons in an atom. So with this, the lowest energy level available to an electron is going to be what's known as the ground state. And then the excited state is just going to be when we take that electron, give it higher energy, and then move it to a higher energy level. And then this process is going to be kind of similar to what actually occurs in fireworks. And then if you've ever seen me do the flame test, where we kind of just take a few wooden splints, dip them in different solutions, and then place them in a Bunsen burner, different elements are going to produce a different colored flame, a characteristic flame color. Because with it, remember, these energy levels are going to be at specific energies. So what we're going to see is as we take these electrons from the ground state and give them higher energy, so like in the case of putting them in the Bunsen burner, we're giving them higher energy. They're going to move to a higher energy level then. But that's going to be a little bit unstable. Remember, everything in the universe wants to go to lower energy. So the electron is then going to do what's known as relaxing. It's going to go back to that ground state. It's going to have to release or emit that energy that it gained. And because these energy levels themselves are going to be very specific energies, the change in energy, delta E here, is also going to be a very specific amount. So the wavelength of light being produced is going to be characteristic for that element. So that's why if you're looking at fireworks, they can determine, or they know what color is going to be produced, because they can use a different substance that's going to have an energy transition that'll give us the wavelength that we're looking for red or green, blue, whatever color it's going to be. And then again, the flame test in the lab, just using the Bunsen burner, is essentially showing us the same thing. And with that change in energy, we've got a very similar equation to the previous one that we just looked at. But we can calculate the change in energy as an electron moves from one energy level to the other, using the equation we have here. And then with it, M and E, so we've got a couple variables here. So pi, of course, just the value of pi. H is still Planck's constant. N1 and N2 will be the energy levels. But M and E are going to refer to the mass and charge of the electron itself. But one issue with the Bohr model is that it kind of breaks down. It's not as effective when we get into the larger atoms, so multi-electron atoms. So when we've got more than one electron present, think about it, now there's going to be interactions between those different electrons. There's going to be some repulsion force between them, and that's going to affect the the electrons. And then also with the movement of these electrons, the Bohr model just isn't perfect with that as well. But when we were thinking about the electromagnetic radiation, of course, it behaves like a wave. And then we saw that it can also behave like a particle. So it's got that duality. Louis de Broglie was just a scientist. And he came up with this idea or this theory that a similar sort of concept could be applied to all matter. So of course, matter is going to be behave like a particle. But he also came up with this equation that explains the wave behavior, the wave properties of that matter as well. So the wavelength of any object is going to be equal to Planck's constant over the mass of that object in kilograms. And then with this one, just to distinguish it, this is going to be V for velocity, not V for the frequency. So when we look at the units here, oops, when we look at the units, let me get the draw tool. We'll have joule seconds on the top, and with a joule, that's really going to be a kilogram meter squared per second squared. And then we'll have that entire thing multiplied by seconds on top, just because Planck's constant is joules times seconds. And then on the bottom, we'll have kilograms, and velocity is going to be meters per second. So if we look at what we have here, seconds on top is going to cancel one of the seconds in that. And then the seconds on the bottom will cancel the other. So we'll completely remove seconds here. Kilograms is going to cancel. And then with the meter, we've got 2 on top, 1 on the bottom. So the meter on the bottom is going to cancel one of those meters on top. And that's why with the wavelength here, we're going to see it's equal, or the unit where it will arrive at is just going to be meter for this equation. So if we know the mass and the velocity of any object, we could determine what the wavelength of that object is going to be. And then if we think about electrons, like I said, those are going to be a particle, but we'll also be able to, or we'll also see that they'll behave similar to a wave. And then with it, we've also, again, just got the principal quantum number here, referring to the energy level. But the way that they could kind of prove that the electrons can behave similar to a wave is they took an X-ray and then had it pass, or X-rays, and had them pass through thin aluminum foil. And they were able to produce this pattern here. So we've got the circles. And then they did the same thing with a beam of electrons. And you can see we see a very similar, of course, not exactly identical, but we see a very similar pattern here in terms of the placement and the size of these different rings. And again, that's going to be because we've got that duality where these particles, where these electrons, much like the electromagnetic radiation itself, can behave like a wave and can also behave like a particle. And then where did I want to stop for this one? And that seems like a good stopping point for this one, actually. So with the next one, we'll start to see a little bit more with those quantum numbers, what they refer to, and how that kind of tells us information about the location and the energy of that electron.